Now we come to airflow. Airflow has to be one of the single most important yet overlooked parts of the heating or cooling system, no matter when they're being put in. And that's a shame. Guys like myself that have been in the industry for a long period of time, yet started clear back in the 90s or 80s or before, may have never actually had the proper teaching to learn how to check airflow, to properly learn how to use a blower performance chart or a manometer to aid in their diagnostics for airflow. We're going to talk about that right now because I place a fundamental core value on this subject. So in looking at airflow, there's a couple of things you got to think about. First of all, you've got to make sure that the filters are correct. They've got to be the correct filter for the application, the correct size for the application. If either of those things are wrong, it doesn't matter where you have things set. You may not have the proper airflow no matter how you look at it. You've got to make sure that the filters aren't too restrictive. Now, there are some filters that came out in the late 80s, maybe mid 90s. We used to call them Paul Harvey specials. They were washable filters, extremely tightly woven, crosshatch with plastic mesh with some foam in between them. They were so restrictive that you could literally take and put a water hose up next to it and nothing would come out the other side, maybe a little drizzle. So you know airflow is not moving through there. Restrictive filters are probably one of the easiest things to correct on the job site that will make the biggest impact on the customer's comfort level. Is the blower wheel clean? Now, ASHRAE and Energy Star both place a number on the percentage of decrease in airflow on the return side or the supply side as to whether or not it's going to affect the rest of the system. And that's 10%. A 10% restriction on either the supply side or the return side, both can be affected by the blower wheel, can affect the overall efficiency and capacity by up to 50%. That is so huge and such an easy thing to fix and to cure as well. And you think about it, 10%. That's a dryer sheet getting stuck in the filter. That's a restricted secondary heat exchanger that rests above the blower wheel. That's the blower wheel itself, those little scoops that have barely a turn on them, getting a little bit stopped up with dust or hair. Those things make a huge difference. And if you've got to dismantle that blower housing, take the motor out of there, take the wheel off the motor and wash it out, and that's going to be the difference for the customer, you've got to take care of that. Is the evaporator clean? We don't have as many evaporator issues now as what we used to because we have a secondary heat exchanger now that rests just above that blower. And so oftentimes the secondary heat exchanger is going to catch all of the junk that used to get caught in the evaporator coil. However, anything that gets past there that's a much smaller particulate like dust and pet dander and things of that nature are going to catch on a nice wet coil. So the evaporator coil can still get dirty, and especially if you're using filters that are the least amount of restriction, which are those fiberglass filters. You know, that's what the manufacturer gets the efficiency ratings with. That's what gives you the best airflow, but that also, on the opposite side, is the least effective on the filtering side of things. But you can't take that into consideration because these furnaces were never meant to filter the air. They're meant to move the air so that we can create a comfort level through our heating and cooling system that's sufficient for the customers and efficient for the home. Are the registers open? Now think about that. If you're only closing 10%, the average home has somewhere around 25 to 30 registers. That's 3 registers in a home that are closed. Probably most of the homes that you go in will have registers closed in them. It doesn't take much to create a negative effect in closing those registers. If you're not able to move that air down those runs, that does impact everything else. Now think about it. People close off the registers in order to attempt to force the air in a different direction or to a different portion of the house. Okay, true. Now, if that's the case, wouldn't it always work? Well, that's a loaded question. That's a tough one. It depends on the type of blower. Now, if you've got a multi-speed blower, the multi-speed blower doesn't know that you've closed all those registers. It's still trying to push down those runs. And just because you close off those registers doesn't mean the airflow is automatically going to go to a different run, say to the second floor or to the weird bedroom above the closet or to the new addition that you've put in that never had good airflow. It just doesn't work that way. The variable speed technology does help in that a little bit, but if you're restricting that airflow by closing the registers, you have unintended consequences of doing that with a variable speed blower, because once you start restricting that, the amp draw goes up and it starts to cost you some more money. And that's originally why you got that variable speed blower in the first place, was one, to push the airflow, of course, but two, to save you money. No, it's only going to save you money if it's in the proper application, and restricting it is definitely not the proper application. So look at this blower wheel. I've got a couple of fun pictures here. This was an actual picture that was taken by one of my good friends in the technical department of a wholesale house. He goes out to a customer's job site because the customer wanted to claim warranty on an air conditioning system that had a coil that continued to freeze up. They'd gone through a couple of different expansion valves. They pulled the coil out. It's not stopped up. So here's the long story short. Customer has an existing furnace. The old air conditioning system wasn't working properly, so the contractor sold them on replacing it and putting in a new air conditioning system. This was a condenser, a coil, line set, expansion valve, all of that. So they get the job done, and when the job is done, the new system is working very similar to what the old system was working like. And that was obviously a problem for the customer. They just got done spending a ton of money with the contractor, and the contractor was at a loss. So they replaced the expansion valve more than one time. And finally, they just wanted warranty on the whole thing, wanted their money back. They wanted to go with a different brand. And so the technical advisor gets involved, goes out there. First thing that he looks at is the surroundings, right? What's around that coil? What's around that condenser that could affect the way it operates? You know, and this is just it's a different mindset. Some people don't think that way, but the problem isn't always with the mechanical appliance that is showing the problem. Sometimes the problem is with the surroundings. And so he begins to look at some of the surroundings. And one of the beginning things, of course, was the filter and the duct work and all of that. But then he opens up that bottom panel and looks at the blower, and the blower wheel is completely full of hair. Now look at this thing. That's pretty next level. And so at that point, obviously, the contractor was a little embarrassed. But think about this from a homeowner's perspective. Now, how would you think that contractor treated you? If that contractor was having problems with the old air conditioner and couldn't get it fixed and replaced it, and the new air conditioner is having the same type of problem, which was freezing up and airflow issues, and then you see this, which directly ties into both of those issues, maybe you're thinking that you got sold a bill of goods, and you didn't actually need the air conditioning system in the first place, and it was a simple maintenance related issue that could have been solved, or that could have solved the problem much less expensive. That's a conversation I don't want to have, and I'm sure that you don't either. Here's another fun picture. Now this is fun for us, but it wasn't fun at the time. This is just the opposite. Here we have the technical advisor going out on a job in which the furnace, brand new furnace, kept trip and limit. Nothing that they could do to get this thing to quit trip and limit. Well, it was your standard installation in which the furnace was going to be replaced, but not the coil and not the air conditioning system at all. So what they did is they go out there and they strap up the plenum with wire, so that way it stays in place as they pull out the furnace underneath. And rather than just stick your head under there and look up to see whether or not that coil has stuff that you could clean out of it while it's now wide open, they didn't do that. They got ahead of themselves and moved much more quickly than what they should. And instead of finding this mess, what they actually did is just shove the new furnace under there, left that coil where it is, didn't check it out, and built the plenum down to the top of the furnace, and then ran the furnace. Couldn't figure out why it tripped limit. Well, it couldn't get rid of the airflow, and that's a big problem. When you can't get rid of the airflow, you can't get rid of the heat. So you've got to think about those things when you're out there. Think about how quickly this problem could have been solved during that installation. Now, sure, it might slow you down for 10, 15 minutes while you clean this thing out, but that's not nearly the amount of time that was spent afterwards in the several trips and also getting the technical department and almost the manufacturer involved with the situation and getting egg on your face because in reality, the problem was yours, not the equipment at all. So checking the airflow. Hey, here we are talking about air conditioning systems and checking the airflow. And we hear terms like external static pressure or ESP thrown around all the time. So what does that actually mean? Well, ESP, the external static pressure, basically static is a fancy word for resistance, right? So we're looking for resistance external to that furnace. So everything that is before the furnace, including the filter and all the ductwork, and everything that's after the furnace, including the coil and all the ductwork, are all included in this measurement. Now, if you look at where the two white holes are in this furnace, they could be symbolic of the side of the furnace or the back of the furnace. You could make those two penetrations actually in different spots. I've seen people, and I myself have gone in through the high limit switch, remove the high limit switch. We're not running this on heat or cool. We're only using the fan auto speed or potentially just setting up dip switches. So you could go in through the high limit switch, and I've seen people go into the before the blower section with taps that go in through the low voltage side of that cabinet. So there's other places that you could go. This is symbolic really to show you that you have to take a measurement before the blower, you have to take a measurement after the blower, and that's got to be in the furnace cavity, so it can't be outside of that. So what is that going to actually do? That's going to show you on your manometer how much resistance is placed on everything after that furnace and before that furnace. How much stress is that blower really under? Because the manufacturers have a specific value that they're looking for. Almost all manufacturers across the board are going to give you a value of 0.5 inches of static that you're shooting for. Okay, but if you look at this chart that we have here, that 0.5 inches of static is on the right-hand side of center. You could actually go up to 0.8 inches of static on this, as well as most other manufacturers that have multi-speed blowers, and still be within a verifiable range. And the idea here is to check the static before the blower and after the blower, add those values together as raw numbers, take them over and to this chart, and plot those across the top of the chart. Okay, so we've got 0.5 inches of static and I'm on low speed. Well, I'd have 674 CFM going through that air conditioner at that furnace at that time. So that's the kind of value that we're looking at there, and we're going to explain this a little bit more, but really this is, in a general sense, some of the baseline information that you've got to know in order to properly set up your furnace. So looking at a blower performance chart, this is another version of the blower performance chart in which you see what's called a fan curve. Those two weird lines in all the checkers there are telling you where that fan is operating as far as CFM goes and static goes throughout the cycle of that fan operating. Okay, so if you look across the bottom, you see the CFMs. Okay, that is airflow and CFMs. We know most manufacturers want you to set up an air conditioning system to operate at 400 CFM per ton on most, Some of them are at 350 CFM per ton. But if you look at the 400 CFM per ton, what that's telling you is a 1-ton unit would use 400 CFMs. A 2-ton unit's 800. A 3-ton unit is 1200 CFM. And you're trying to set it up for that value. Okay, so how do you figure out where that actually leads? Well, if you were to use your manometer and stick it in those areas of the furnace that you made the penetrations in before and after the blower, like we just talked about, you'll find a resistance reading. And on that resistance reading, you then take that back to the chart, and that chart is going to tell you what the CFM value is for that resistance. Okay, and before we move off of this chart, we're gonna talk about this a little bit more, but before we move off this chart, there's something that we really need to address, and that is filters. Okay, one of the biggest problems that we have, we go out and we put in a brand new furnace, and that brand new furnace is set up to the nines by the efficiency programs that are out there, by the standards that the manufacturers give and the industry gives. So we do everything right. When we leave, the customer goes out and buys a $30 really restrictive filter, puts it in place of the one that we have, which is probably going to be either a 4-inch filter or it's going to be a fiberglass type filter. And they totally change all the dynamics because they've really restricted that airflow now. And because they restrict the airflow, the charge isn't going to be adequate. It's going to change the temperature drop across a coil. It's going to change the delivery to the different rooms of the house, all of that. So how do you explain that to a customer? You know, unfortunately, I don't have a good way that you can do that. However, I do have a suggestion that you can get into your own mind, and this may help you come up with a way that you can explain this to a customer. Okay, so bear with me. On the left-hand side of this chart that you're looking at, you see numbers going up and down, and that's what's called static pressure. It's measured in inches of water column on a manometer. Now, static pressure is a fancy word for resistance. How much resistance is in that ductwork, and that's what you're measuring with your manometer. So going up and down that chart, as you go all the way up to the top and you see the number 1, that is 1 inch of static. In most applications, that is way more than you would ever want. Okay, but in this particular example, that's the maximum amount. You can't get any more than that. Okay, but at 1 inch of static, if you were to put a dot right on that line, clear over by 1 inch of static, how much CFM do you have? You have 0. So at the most amount of resistance, you have the least amount of airflow. Now look at it from the other direction. Go down to the bottom horizontal chart. You see those numbers across the bottom, which is CFM. That's how much air is actually moving while that fan is running. The farthest you can go over to the right, let's just say it's the 2200. Okay, you go over to that 2200, that's the fastest this thing is going to ever run. That's taking the blower out of the furnace altogether and setting it out on the floor. It's equally as bad for the motor. It's going to burn itself out because it's freewheeling, but you get my point. Least amount of resistance, so we got 0 resistance, is the highest amount of airflow. So look at it this way. If we put a board, a piece of wood, in the filter box, it's going to catch 100% of all of the pet dander and allergens and dust mites and hair and everything you could think of. It's going to catch all of it. It's a 100% efficient filter. Now, how much airflow is moving through there? 0, right? So we got a 100% efficient filter, but 0 airflow is moving through there. So the closer you get to a piece of wood, the more efficient your filter is going to be, but the worse off your airflow is going to be. And your system is only as good as the airflow. And with airflow being the biggest issue in our systems, you want to have as little restriction as possible with that filter. Now, with that being said, that's a hard conversation to have with a customer. They want the best filter because they want to filter all the stuff out of the air. Unfortunately, sometimes they're willing to jeopardize their $8,000 or $10,000 install with this equipment on a $30 filter because it's a better filter. These systems were never designed to filter the air. Now, there's a reason you can't go down to your local hardware store and get a filter with the same name as your furnace and a 1-inch filter, because those restrictive MERV 11 filters may not be the best thing for your furnace. So you go down to True Value, you might not find a Goodman 1-inch MERV 11 filter. You might not find a Carrier MERV 11 1-inch filter or a Trane MERV 11 1-inch filter because they weren't designed to be in these systems. These systems get their maximum efficiency by allowing the most amount of airflow to go through there, so they move the most amount of air while having it at the right temperature when they're doing it. That helps dehumidify and cool in the summer and heat in the wintertime, but it also, on a larger scope, over the long haul of this system's life, it will preserve that life. It won't be working as hard. It won't sweat in places it's not supposed to sweat. It won't have problems that go unseen for years and years that will eventually lead to large, expensive problems. So blower performance is a huge, huge factor in everything that we do. So here's a more expanded blower performance chart as far as your static pressure chart. If you look over to the left shows you the model of the equipment, and you have to make sure that you're looking at the right model. Okay, for instance, the one that's up at the top there, the GMH 95043BX. It's telling you that you've got your fan speeds set at medium and high. Okay, so your medium is going to be your furnace speed on high, and then your high speed is going to be your air conditioning speed. Is that going to be good for every application? Do you just not set it up after that and don't need to check it because the manufacturer knows what they're doing? Well, no, that's not the case at all. That is a very specific setup that's there for the manufacturer, and the days of leaving it the way the manufacturer has it, okay, those are gone by the wayside. So you have to check it. You have to put your static pressure tubes in there, and you have to check everything. Okay, so you check before the blower and you check after the blower. And once you check before and after the blower, then you make your assessments. You add the raw numbers together. Okay, now for those of you mathematicians, that might be a bit of a tough stretch, right? You stick it before the blower, it's sucking, so it's a negative pressure. You stick it in after the blower, it's blowing, so it's a positive pressure. We don't care about the negative and positive. You take the negative and positive, you crinkle it all up, and throw it in the floor because we're adding raw numbers. So in this instance, if you measured your static pressure and it was negative 0.4 before the blower and positive 0.4 after the blower, those don't equal 0 in this particular example. They equal 0.8. And if you look at our example here on this GMH 95, if we had 0.8 inches of static and we were on high speed with this air conditioning system, we'd had 853 CFM. Now, is that the right amount? I don't know. It depends on what size the condensing unit is. Is it a 2-ton unit? Is it a 3-ton unit? Is it a 5-ton unit? Those are what make the difference. 400 CFM per ton. Now, what I like to do is when a system is brand new and I'm installing it for the very first time, I like to check the static pressure on each of those fan speeds and write it next to the fan speed. So that way, one, later on, somebody knows that it was done. And they see the values, they see the work done, they see the penetrations, they know that I did my job. Two, it allows me to come back and make adjustments knowing what those static measurements are. I can quickly see all the CFM values that correlate to the static measurements. Now think about it. You've got 0.8 inches of static on your high speed. Chances are going from high to medium, you're going to be probably somewhere closer or in between the 0.7 and 0.8. Okay, so let's say it drops down to 0.7. Well, check that out. At 0.8 on high speed, it was 853 CFM. but at 0.7 on medium speed, it's 859. It's actually 6 CFM higher on medium speed because of the change in the resistance in the ductwork. Now you go to medium-low, chances are between medium and medium-low, you probably won't drop to another static level, so it'll probably stay right in that same guideline there. So you probably drop down to maybe around 741 in this instance, and then once you drop down to the low speed, you're going to be at that 620 CFM range. Hey, and those are examples. Those are not standard by any means. You know, there is no such thing as standard. Every install is different. Every piece of ductwork in every home is a little bit different. Now think about this. Okay, I'm going to switch gears and I'm going to tell you something, and it's going to correlate to heating, and I think you'll get it. Right? This is how critical it is that we set these up. In the past, some of the older furnaces that we put in had an air temperature rise nearly 100 degrees. Okay, now you take the same BTU value in today's furnaces, our air temperature rise, according to many of the efficiency tests and setup charts, they want you to be somewhere around the 50-degree temperature rise setting. Okay, now the manufacturer has on their tag 35 to 65 or 30 to 60. Okay, but that's an operating range that's safe to operate that piece of equipment. It doesn't tell you anything about efficiency or anything like that. You still got to set it up. Okay, so older furnaces had a temperature rise of around 100 degrees. Newer furnaces of the same BTU value are supposed to be set up around 50 degrees. So what changed? We went from 100 degrees temp rise on the old one to 50-degree temp rise on the new ones. A ton more airflow. That's what we've got to move, is a ton more airflow. So the older ductwork that's in the homes oftentimes is not sized correctly for the modern equipment. It was sized to move less airflow. So we're already starting off with our hands tied on the ductwork, because usually it's all in finished ceilings and walls and floors and things like that. So we have to do what we can to make the airflow right in the home. And what we can do is, one, make sure that the filter is sized properly, and also make sure that it's not restrictive. The fiberglass filters, although nobody likes to use them because, well, you can hold it up like this and see right straight through it, and it's not going to catch much except for the big stuff. Well, you start putting more restrictive stuff in there, then it starts to cut into your airflow and mess everything up. So we can control the filter. We can control the filter both in size and restriction. We can control the return air drop. One of the biggest things that I see as an issue in our industry are the return air drops. 20 years ago, one of the more common filter sizes was a 16 by 20. And there aren't very many manufacturers nowadays that will allow you to use anything smaller than a 16 by 25, up to 70,000 BTUs. And once you get above 70,000 BTUs, or at 70,000 BTUs, well, then you really need to jump up to a 20 by 25 filter. And then at 90,000 BTUs, you need to have a base with a 20 by 25 opening, or you have to have the weird dual side return in there, which always looks a little bit odd. But you've got to make sure that you have adequate return air, and that's one of the easiest things for us to cure is the return air side. Now, that doesn't count putting in more return air registers upstairs as being easy. I'm talking about what's in the actual mechanical room. And the last thing that usually is something that's fairly simple for us to cure is going to be the collars. 20 years ago, you had a lot more dedicated sheet metal workers, and those tinners were very, very good at their craft. And I'm not saying we don't have them now, but the price of prefabbed metal has come down so much that a lot of times, instead of making some of the easier, smaller parts out in the field, they'll go buy a box of them. And so they have them on their van, so it doesn't really, it's not really cost effective to make them like it used to be. Now, 20 years ago, if you had to put a collar on for a run that's coming off the ductwork, the tinner would go ahead and just fabricate that right there on the job, and it would just take him a few minutes to do so, but oftentimes it wasn't going to be an offset, right? So the offset comes off of the ductwork in a slope, right? So it slopes up and then out on your trunk lines. A lot of times in the old days, what they would do is they'd fabricate one that was a right angle, right? Just a nice square collar, which served the purpose just fine. We had less airflow back then, so we didn't have as much of an issue with the duct restrictions as we do now. So to sum it up on what we can fix and what we can do with our ducted systems to provide better airflow is, one, you go out there and you look at a job and you're bidding a job and you're putting in new equipment, or even on a service and check, look at the return air drop. You can get a lot of information from the return air drop. Is it physically sized right? Is it big enough for the return air on the new equipment? Do we have adequate filter space? Meaning, is it at least 16 by 25 or bigger? Now, with that being said, are we doing a 4-inch filter? If we're doing 4-inch filters, 4-inch filters have more surface area, so usually they lend themselves to better pressure drops, and they're not as restrictive as the 1-inch filter. So if you have to have something that's a little bit better filter, you know, instead of going with the 1-inch filter, which has very little surface area and is highly restrictive, you'd be better off to go with a 4-inch filter that has more surface area and less of a restriction in the system. Now, you're still going to have to change it every couple of months. So it's going to cost you still, you know, 20, 30 bucks to do so, but it will filter the air better, and you'll not bite into your airflow as much as a 1-inch filter will. So back on track, we got the return air drop. Is it sized properly? Do we have the right filter in there? And after that, do we have straight collars, or do we have offset or transitions? You know, how is our duct work coming off on our trunk runs? If they're straight collars, we can fix that easy. We can put in offsets. And then lastly, make sure that everything is set up properly. You know, do we have a blower? Is our blower set up the way that it should be? Do we have the right dip switches selected on a variable speed or ECM blower? And then in addition to that, do we have the right CFMs on a multi-speed blower for the amount of tonnage that we have on this equipment? Here's your example. If you look at this, we had 0.7 inches of static on high fan speed, 0.5 inches of static, taking your measurement, of course, before the blower and after the blower. Adding those together, that came up to 0.7. You go over to this chart, 0.7 equaled 955 CFM. Okay, so that is a direct value that is very easy to measure and then also to manipulate, because you can change your fan speed to one lower than that very easily. You just change the speed taps on the blower. Looking at the CFMs, again, when you're taking your CFM static measurements, you're dropping the negative and the positive off, and you're adding just the raw numbers. So like I said, negative 0.4 and positive 0.4, traditionally in mathematics, that would equal 0. But in what we're talking about, you're taking the negative and positive, throwing it on the floor, and adding the raw negative, or the raw numbers, which would be 0.8 in this particular instance. Your fan speeds, traditionally, as we were just looking at on the manufacturer's guidelines that I just had pulled up there a minute ago, you had 4 fan speeds. You had the high, you had the medium, then you had medium low, and then you had low. Okay, so if you look at this board, you've got a spot for your high heat, your cool, your low heat, and then there's 2 up in the top left-hand corner. They're called park. Park is not energized. It's a place for you to put any spare fan speeds that you don't want energized, and it's in lieu of the way we used to do things. The way we used to do things was to just tape it up and leave it hang, or strap it to another bundle of wires. Okay, now you just run that to the board, and that's an unenergized terminal. One thing that you'll find out, once you start actually checking your blower speeds, is that your high heat and your cool speed will usually be very, very, very close to the same speed, and oftentimes will be the same speed. It's not the traditional way we used to do things. Traditionally, High was always cooling, low was always heating. Now they're pretty close to the same in most applications, and that's because nowadays we're doing load calculations, and the load calculations are very precise on BTUs for loss and gain on both heating and cooling side, and so it's an interesting thing once you get to starting checking these things. Now, I told you also that one of the things that I like to do is check all the fan speeds really before I begin my setup. Checking all the fan speeds on a multi-speed blower with a board such as the one that we're looking at right now is very simple. The cool terminal on there is what's directly connected to the fan on switch on the thermostat. So if I connected the fan on switch, or I jumped out the R and the G on the board, it would turn on the speed that's on that cool terminal. So as you might guess, what I will do is I'll put my manometer in those two penetrations, the one before the blower, the one after the blower, and I will go from one fan speed, turn it on, write down the static measurement, pull it off and swap it out with another one on the cool, and then I will go to that one and then write it down, and then I'll swap it out with a different one yet, and I'll go from one to the other on that cool terminal, turning the fan speed on, so that way it's very quick. I'm not using heat or I'm not using cool. I'm just looking at the raw values for the static and the ductwork. That's all I'm looking for, so I can properly set up that blower. Okay, and there's a little bit closer look at what we're talking about. Okay, this one's a little bit different because here we actually have a control board for a more advanced system that has an ECM motor or a variable speed motor. And you can see on the left-hand diagram out of the manufacturer's installation instructions, there's some switch banks there. And ironically, the way that those are labeled is S1, S2, S3, those are switch banks. And they don't necessarily always work out that way. As you look at the actual control board that I took a picture of here on the right-hand side, if you look close, in the upper left-hand corner of each of those switch banks, they're not in order. The one at the very top, spaced away from the other three, is S3, so switch bank 3. Then after that comes switch bank 4, and then 5, and the one very lowest on that totem pole is switch bank 1. Now you can see that those switches on those switch banks, they go in one position to the other position. One side's on, one side's off, and different configurations of on and off give you different values in programming for how the controls in the rest of that furnace operate, particularly in this case for our variable speed motor. Okay, here's an example of the manufacturer's diagrams on how to adjust the blower speed. Okay, if you look at the switch banks at the top, we got switch banks 1, 2, and 3. And if you look at the cooling selections here on the little breakaway chart, just off of the left-hand side of where I am, which is right over here, you'll see the cooling selections. And they tell you whichever size blower you've got, that's going to be the corresponding CFMs for your configuration of dip switches. Okay, so if you've got the 56,000 or the 70,000 BTU furnace, then you're going to have a half horse blower, and your configurations of switch bank 1, dip switch number 4, and dip switch number 5, both in the off position, will be 1,050 CFM. But if you had the larger size furnaces, the 84,000 and 98,000 BTU furnaces, then you're going to have the 3/4 horse blower, and that same configuration of dip switches, switch bank 1, dip switches number 4 and 5, will then equal 1,750 CFM. Okay, so you have to make sure that you've got the right blower that you're looking at here as far as your terminal settings and when you set up your dip switches for an ECM motor. Now, it's not rocket science. And some people set these up and they say, well, how do I know that it's actually achieving that? Okay, well, here's a secret. These things are pre-programmed to achieve the CFM value that you set them at as long as you're less than 1 inch of static. So that control module that's on the end of that motor will maintain that 1050 CFMs on the off-off configuration for the half horsepower blower unless you go over 1 inch of static. Okay, so your measurement before the blower and after the blower has to be less than 1 inch of static in order to maintain that 1050. Now, once you get up above that 1 inch of static, it goes all over the place. It's just, you can't say that it goes down, it goes up. It's kind of a mixed bag. But one thing's for sure, the farther away that you can keep it from 1 inch of static, the better off you are. Now think about it. Okay, you've got a motor with a computer module at the end of it. And that motor with a computer module at the end of it is consistently trying to fight the resistance in that ductwork. And the way that it does that is it's changing its configurations internally to increase the amount of torque that it can exert against that resistance. In doing so, the amp draw goes through the roof. So you've got a motor that's extremely efficient as long as it's in the application that it was designed for, which is 1 inch of static or less, and according to manufacturer specs, 0.5 inches of static or less. If you put it in that application, it will run much more efficiently than its counterpart in multi-speed blowers. Again, here's your blower chart. Your blower chart that we just spoke about a second ago. Not a lot of rocket science here. I did want to make sure that we got one more look at it so that everything was crystal clear. Okay, so things you need to look at. You got your correct model number, okay, over on the far left-hand side here. You're on X fan speed, and that X fan speed correlates to your resistance across the top, right? Your static. So that would be the 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Okay, that's your measurement of before a blower and after the blower, and you add the raw numbers. Okay, once you figure out what those are for each fan speed, you go to that static resistance, go down the column, match it up with its corresponding CFM value, and set up your blower according to 400 CFM per ton for this manufacturer, and for most manufacturers, or 350 for just but a few of them. But know what the manufacturer actually wants and set up that blower speed according to that. If you don't do that, what happens? If you don't set up your blower speed properly, well, then what? I'll be honest with you, I went over a decade not understanding any of this stuff. So what happens? What happens to those air conditioning systems? Well, almost every one that comes from the manufacturer has high speed as your air conditioning speed. Okay, so if high speed is your air conditioning speed, and that's way more CFMs or airflow than what the system actually needs, what happens is it makes your coil too warm. It takes the cool away from your coil too quickly, so you don't get good dehumidification, you don't get a good air temperature rise, or I'm sorry, air temperature drop across that coil. So what you do, instead of lowering the blower speed like you should to the correct CFM value, you go out and you add refrigerant to the system outside. And when you add refrigerant, it fills that coil a little bit more and creates a little bit better temp drop. Never perfect, but in doing so, it gets it to the point to where it's working fairly well, but over the long haul, here's what happens. It doesn't dehumidify properly. You've now overcharged the system, so it's not running efficiently. You've ruined some of the capacity, some of the efficiency. The compressor is not running, electrically speaking, as efficient as it should. It's going to draw more amps on startup, so the likelihood of it tripping a breaker or blinking the lights is much higher than what it would be if you'd just done it the way that you should have done it. And all around, those things are going to probably add up to a system that dies or has a failure rate well before its time. And the best case scenario, you're going to have a system that is going to cost the customer a bunch of money over a long period of time because it's not running as efficiently as it should, and it doesn't have the capacity to now cool the entire structure the way that it should. So it always will struggle. Okay, so here's another little secret. Those problems only show up in extremes. You ever wonder why it gets so busy when it's 95 degrees, but when it's 87 degrees or 85 degrees, it's not really all that busy at all? Well, because at 85 degrees, you turn a box fan on in your room, a box fan feels pretty good. You can cool a home that's at 85 degrees at least enough to make the customer or yourself feel like everything's working the way that it should. The wheels are all spinning, and not enough to complain, certainly. But once you get up above the 90s, into that 95 degree plus range, all the little things that you didn't do correctly when you were out there servicing it or initially installing it, that's when those things show up. The extremities. Your furnace problems always show up at below freezing. Your air conditioning problems always show up in the 90s and above, because that's when all of those problems are exposed. When it's 90 some degrees in the Midwest, it's also really humid. At 85, sometimes people still have their windows open and you get a nice breeze across the house. But at 95 degrees and humidity added into that mix, it feels like it's into the hundreds. So if you're not dehumidifying properly, because it's not charged properly and the airflow is not set properly, that sticks out. And then you run into a situation where maybe you have some cool air, but it's cool and it's clammy, so it's a little moist. It's not dehumidifying. You run into kind of a funky smell as well.